Welcome to this session on drilling optimization, focusing on Total ROP, enhancing techniques and technologies, part of submodule 3 of 4. In this module, we'll explore how real-time monitoring of drilling parameters improves performance, reduces risks, and ensures safe operations. We'll also look at advanced technologies and methods that enhance drilling efficiency. Let's begin by reviewing our objectives. In this submodule, we will focus on drill string mechanics monitoring and its critical role in optimizing drilling operations. Our first objective was to understand how drag and torque measurements are monitored, calibrated, and used to predict performance in future wells. We achieved this by examining field data calibration, torque, and drag modeling, and the application of broomstick plots in practice. The second objective was hazard avoidance through hole condition monitoring. We covered surveillance tools such as friction comparison, hook load modeling, surge and displacement models, and slack-off fingerprinting, all of which help detect early warning signs of trouble. The third objective was to evaluate technologies like DBOS, IDEAS, and OptiDrill. We discussed how these systems apply geological data, advanced modeling, and real-time optimization to enhance drilling performance and reduce risk. Finally, we set out to recognize friction factor trends. This was addressed through the exercise interpreting pickup, slack-off, and rotating weights to identify issues such as poor hole cleaning or differential sticking. By the end of this session, you'll understand how drill string monitoring drives safe, efficient drilling. In drilling mechanics monitoring, we start with drag measurement and friction factor calibration. By measuring drag during tripping operations and calibrating against modeled predictions, we can improve the accuracy of engineering forecasts for future wells. Torque measurement follows a similar process, enabling prediction of downhole behavior and mechanical loading. Trajectory planning execution is another key area. By monitoring borehole tortuosity, identifying points of contact, and correcting using directional drilling indices, we can limit excess drag and reduce mechanical risk. Next, hydraulics and buoyancy must be considered. Cuttings, loading, and fluid-specific gravity directly affect effective weight on bit and friction factor. Monitoring these in real time ensures more accurate drilling predictions. Now let's look at the practical aspects of drill string mechanics monitoring. We start with drag measurement and friction factor calibration. By measuring drag during tripping operations and calibrating against modeled predictions, we can improve the accuracy of engineering forecasts for future wells. Torque measurement follows a similar process, enabling prediction of downhole behavior and mechanical loading. Trajectory planning execution is another key area. By monitoring borehole tortuosity, identifying points of contact, and correcting using directional drilling indices, we can limit excess drag and reduce mechanical risk. Next, hydraulics and buoyancy must be considered. Cuttings, loading, and fluid-specific gravity directly affect effective weight on bit and friction factor. Monitoring these in real time ensures more accurate drilling predictions. We also account for the rate of penetration optimization at the bottom, BHA rotation limitations, and vibration modes, axial, torsional, and lateral, all of which impact performance. On the top of the slide, you'll see a broomstick torque and drag diagram. This visual highlights calibration of friction factors, showing how field data is matched with modeled lines. By interpreting deviations, we can identify problems such as cuttings buildup or excessive contact points. To the right are chemicals used to reduce the friction factors, and at the bottom are tools such as the roller reamer that helps to reduce friction, vibration, and borehole when reducing rugosity. Altogether, these elements build a robust case for drill string mechanics monitoring. Next is a video on Encapso. This was a product in development with SLB fluids to provide improved lubricity in water-based mud system.
Global energy demand continues to rise, but known fossil fuel reserves are more difficult than ever to recover, requiring new technologies and more drilling activity, placing increased pressures on the planet.
Solozyme has spent over a decade and over $500 million developing a technology platform to solve some of the biggest problems facing our planet, first and foremost, energy.
The challenges for the drilling industry are significant. Drilling deeper and drilling horizontally through harder rock takes more energy, time, and precision. Increased use of harmful drilling chemicals creates additional environmental risk. In standard drilling practice, increased friction slows down operations. Mud engineers react by adding a slug of liquid lubricant. These conventional liquid lubricants seep into the rock formations, are pulled out in drill cuttings, and can lose effectiveness while circulating. What's more, lubricant loss increases drag and torque, putting expensive equipment at risk. All of this adds cost, which leaves the industry looking for a high-performance solution. To meet this need, we've developed Encapso, the world's first encapsulated biodegradable lubricant, designed so customers can drill faster, straighter, and cleaner. Encapso's shell protects the high-performance liquid lubricant inside. Encapso is proactively added to the drilling fluid at the onset of operations, before problems occur. It circulates freely as an inert ingredient without seeping into formations, sticking to drill cuttings, or losing effectiveness. When Encapso encounters friction, it activates, delivering a high concentration of lubricant. In comparison with traditional lubricants that are more dispersed and lost in the system, Encapso's targeted delivery means more lubricant exactly where and when you need it. And if you don't need it, Encapso can be reused in subsequent wells. Encapso means reduced environmental impact, minimal waste, lower costs, and higher performance. Developed through Solazyme's groundbreaking biotechnology platform, Encapso can be programmed for customer needs by increasing or decreasing the strength of the shell. Encapso can also be tailored to contain different amounts and types of liquid lubricant for a variety of drilling needs. Encapso's efficacy has been demonstrated in both the lab and field, including a rig test with Frank Hsu, one of the inventors of horizontal drilling.
In our testing, Encapsa demonstrated its ability to reduce friction, reduce the drag, decrease the torque, and improve the penetration rate. It is a revolutionary formulation.
Because it is liberated at the point of contact, I may be able to drill this well with 2 bits instead of 5. Well, every time I trip a bit out of the ground, it costs me $1 million.
I introduced Encapso to a few customers and worked with them on several wells that they were drilling. In all cases, we witnessed marked improvements in directional control. We saw an 11% average reduction in torque and an increased borehole quality.
What impressed me about Encapso most is the ability for me to do what I need to do in the shortest period of time. It also translates into money because time is money.
After adding Encapso to the system, we saw a rate of increase in our rate of penetration from 2 feet per hour to 40 feet per hour. Encapso is a game changer because you're reducing your torque, you're reducing your drag, you're reducing your coefficients of friction all at the same time. No other product on the market does that.
The world's appetite for energy just keeps growing, and Solazyme has developed a new solution, Encapso, to help reduce the costs and the environmental footprint while helping meet this increased demand for energy.
The logs show an approach to hazard avoidance through real-time monitoring of hole conditions. One important method is comparing friction factors with previous trips shown on the left log. By looking for increases in drag or torque compared to the last run, we can quickly identify deteriorating conditions such as poor hole cleaning or developing tight spots. We also use hook load models in the time domain. By simulating expected hook load responses during tripping, and comparing them with actual field data, we can spot anomalies that suggest restrictions or cuttings build-up. Surge effect models are also critical, as they predict how fluid pressures change when moving pipe in and out of hole. Exceeding fracture gradients or swab-induced kicks can be avoided when this is modelled accurately. Another surveillance tool is pipe displacement models. By comparing theoretical versus actual displacement, we can detect obstructions, excessive cuttings, or differential sticking risk. Slack-off load fingerprinting also provides insight. By analyzing the transfer of weight from hook load to bit weight, we can identify depth-related friction and potential sticking zones. On the right-hand side of the slide, we see diagrams showing actual versus modeled runs, including surge effects, volume corrections, and slack-off fingerprints. These visuals confirm the importance of comparing real-time data against baseline models to avoid hazards. Next, we'll look at advanced technologies to improve performance. Drill Bit Optimization System, or DBOS, as an example of software designed to enhance bit selection and drilling efficiency. DBOS integrates geological data from wireline and logging while drilling tools, often using offset well information. By characterizing rock properties, such as unconfined compressive strength, porosity, and abrasiveness, the software can predict drilling challenges in advance. Using these formation characteristics, DBOS helps engineers select the most appropriate bit design. That includes choosing the right cutting structure, hydraulic nozzle configuration, and gauge protection features. For example, a hard abrasive formation may require polycrystalline diamond cutters with reinforced gauge pads, while a softer porous interval might call for a more aggressive bit profile. The diagram on the slide illustrates how DBOS consolidates available well data and presents it in a decision support format. By eliminating guesswork, DBOS reduces reliance on field trial and error, lowering overall bit costs and improving drilling performance. This approach demonstrates how data-driven software solutions can transform drilling outcomes, moving from reactive adjustments to proactive engineered planning. In the next slide, we'll expand this discussion by looking at dynamic modeling technologies that optimize the entire drill string, not just the bit. Here we focus on the Integrated Dynamic Engineering Analysis System, or IDEAS, which is an advanced modeling suite. Unlike static planning tools, IDEAS delivers time-based four-dimensional simulations that represent the full drill string and wellbore geometry from the bit to the surface. This system applies solid mechanics and finite element analysis to capture dynamic interactions between the bit, the string, and the rock. It allows us to evaluate bending moments, stick-slip behavior, and the impact of dogleg severity on the drill string. By modeling these effects in real time, IDEAS reduces the need for costly trial and error field testing. Below we see examples of stick-slip and bending moment illustrations. These visuals highlight how the system tracks dynamic loading and vibration responses. By simulating how the BHA will behave under different weight on bit and rotary speed combinations, IDEAS can identify risk zones before drilling begins. The true value lies in customization. IDEAS enables us to design bits, mills, and cutters that are optimized for specific applications based on predicted downhole mechanics. This leads to greater drilling efficiency, fewer non-productive events, and safer operations. Building on this, we next turn to hazard avoidance through real-time parameter optimization. Here we see how real-time optimization of drilling parameters can prevent incidents caused by vibration. Downhole vibrations, whether axial, torsional, or lateral, can quickly escalate into severe dysfunctions if not controlled. By monitoring surface and downhole data streams in real time, we can detect early warning signs such as oscillating torque, fluctuating hook loads, or abnormal standpipe pressure patterns. When these indicators are spotted, the system suggests corrective actions, such as adjusting weight on bit, rotary speed, or flow rate, to bring drilling parameters back into the stable operating envelope. The log shows how vibration zones are mapped against operating parameters. It illustrates safe versus unstable regions, guiding drillers on where to maintain RPM and weight on bit. This visual helps explain why a proactive approach is essential. Once severe vibrations develop, damage to tools, connections, and even the bit can occur within minutes. The key message is that continuous monitoring and adjustment, supported by real-time optimization software, protects both the equipment and the wellbore. With these safeguards in place, we can reduce costly downtime while extending tool life. Next is a video on OptiDrill, a solution that embodies these principles in practice.
This service integrates data from the downhole sub with data from surface to provide actionable information at the rig site. The real-time drilling dashboard helps you optimize drilling parameters and intervene early, reducing the probability and severity of undesirable events. When the bottom hole assembly crosses a formation boundary, whirl, bit bounce, or stick slip motions can occur. In this case, backwards whirl is occurring and is immediately detected by the service. A real-time summary of the motion appears on the rig site display, alongside a recommendation to stop and then restart at a lower surface RPM to mitigate the risk. Annular and internal pressure and temperature measurements help to identify and mitigate poor hole cleaning and maintain wellbore stability. High-resolution bending moment provides information about the curvature of the borehole, enabling delivery of a smooth wellbore. Downhole weight on bit and torque measurements are used to monitor the bit-rock interaction and improve ROP. They also provide early indication of changes in borehole friction to avoid stuck pipe. Data from the OptiDrill service is transmitted to surface for use by the rig site team and interpretation by remote experts. The experts collaborate with the drilling team to reduce risk, improve drilling performance, and manage borehole quality. OptiDrill Real-Time Drilling Intelligence Service.
Here is a friction analysis exercise. We are asked to interpret what happens at points A, B, and C based on the behavior of pickup weight, slack-off weight, and rotating weight. At point A, we see pickup, slack-off, and rotating weights moving together. Indicates consistent reduction in friction. The reduction in friction may be due to a mud weight change impacting buoyancy, or the addition of a lubricant, or a change in trajectory compared to modelled. At point B, pickup and slack-off diverge. This typically indicates poor hole cleaning. When cuttings accumulate, slack-off weight increases disproportionately, while pickup weight remains lower, creating a widening gap. The solution here is to improve hole cleaning by increasing flow rate, adjusting mud properties, or performing wiper trips. At point C, pickup, slack-off, and rotating weights rise together. This is a warning sign of differential sticking risk. When all loads increase in unison, it indicates significant contact between pipe and borehole wall, often caused by mudcake adhesion. Preventive measures include reducing overbalance, improving filter cake sealing, and preventing the buildup of filter cake. Let's revisit the objectives we set out at the start of this sub-module and review how we've addressed each of them. Our first objective was to understand how drag and torque measurements are monitored, calibrated, and used to predict performance in future wells. We achieved this by looking at field data calibration, torque and drag modelling, and how broomstick plots are applied in practice. The second objective was hazard avoidance through hole condition monitoring. We covered surveillance tools such as friction comparison, hook load modelling, surge and displacement models, and slack-off fingerprinting, all of which help detect early warning signs of trouble. The third objective was to evaluate technologies like DBOS, IDEAS, and OptiDrill. We discussed how these systems apply geological data, advanced modelling, and real-time optimization to enhance drilling performance and reduce risk. Finally, we set out to recognize friction factor trends. This was addressed through the exercise interpreting pickup, slack-off, and rotating weights to identify issues such as poor hole cleaning or differential sticking. That brings us to the end of submodule 3 of 4 on Total ROP enhancing techniques and technologies. We've examined drill string mechanics, hazard avoidance, and performance technologies, along with practical case examples. This submodule is now complete. Please proceed to the quiz to test your understanding of the material. Thank you for your attention and participation.